March 1, 1910, Culebra cut, Panama Canal zone. The engineering report from visiting British specialists would never fully capture what they witnessed that steamy morning. American steam shovels, moving dirt at rates that defied everything European engineering doctrine said was mechanically possible. Through the jungle heat and mechanical thunder, 95-ton Bucyrus steam shovels carved through solid rock with precision that seemed impossible to European observers. No delicate French equipment, no careful excavation methods, no acceptance of the limitations that had killed 22,000 workers and bankrupted the French Canal Company. In European construction sites, steam-powered equipment lasted mere months in tropical conditions before breaking down completely. Each machine required constant repairs, specialized parts, and expert mechanics flown in from Europe. Most carried maintenance costs that made projects financially impossible. The Americans were operating with engineering philosophy the Europeans had declared fundamentally flawed. Standardized parts, mobile repair shops, systematic maintenance schedules. Machines designed not just to work, but to keep working for decades. 8,000 miles from European workshops, the most decisive engineering revolution in construction history was proving itself, not in superior craftsmanship, not in premium materials, but in the systematic durability that would make these American steam shovels outlast the very engineers who built them. The cable from Paris arrived at the White House on a gray November morning in 1904, carrying news that would reshape American ambitions forever. The French Compagnie Universelle du Canal Interocéanique had officially abandoned the Panama Canal project after 23 years of catastrophic failure. 22,000 workers dead from yellow fever and landslides, $287 million in investor losses, 30 million cubic yards excavated out of the 240 million needed. Ferdinand de Lesseps, the engineering genius who had sliced through Egypt's Suez Desert like cutting butter, stood defeated by Panama's jungle mountains. In his final report to French shareholders, de Lesseps wrote with bitter honesty that few engineers had ever displayed in public defeat. Suez was a ditch through sand at sea level. Panama is a mountain range with a river running through it, demanding excavation deeper than any project in human history. The man who had connected Europe to Asia through pure engineering audacity admitted that Panama required something beyond European capabilities, something that perhaps no civilization possessed. The numbers painted a picture of engineering horror that made seasoned construction experts question whether connecting the Atlantic and Pacific Oceans was physically possible. The Culebra cut alone, the canal's deepest section through Panama's continental divide, required removing 100 million cubic yards of solid rock and clay, more material than the entire French project had attempted. The geology reports described layers of unstable shale that collapsed into freshly excavated areas faster than crews could remove debris. Rainfall averaged 105 inches per year, turning construction sites into swamps that swallowed French steam equipment within months of tropical deployment. French excavation equipment, designed for European conditions, proved catastrophically inadequate for Panama's reality. Their largest steam shovels weighed 30 tons and moved 2 cubic yards per scoop. In France's temperate climate, these machines represented cutting-edge technology. In Panama's crushing humidity, they broke down weekly. Replacement parts took 4 months to ship from European factories. French engineers calculated that completing the canal using European methods and equipment would require 80 years of continuous excavation. British engineering experts studying the French failure reached even grimmer conclusions. Sir William Henry Preece, president of the Institution of Civil Engineers, published his assessment in London's engineering magazine with mathematical precision that left no room for optimism. The Americans possess admirable energy, but lack the systematic precision required for projects of this magnitude. The jungle climate will destroy their machinery within months, exactly as it destroyed superior French equipment. The landslides make permanent excavation impossible using any known methods. European engineering doctrine, refined over centuries of cathedral construction and railroad building, operated on principles that Panama's geology seemed designed to mock. European methods emphasized precision craftsmanship, individual mechanical expertise, and equipment designed for specific local conditions. Master engineers trained for decades in theoretical mathematics before attempting major projects. Every machine was custom built for particular sites, with replacement parts manufactured individually by specialized workshops. Theodore Roosevelt read these European assessments with the stubborn determination that had driven him up San Juan Hill and into the presidency. The man who had declared that America would speak softly and carry a big stick saw Panama as the ultimate test of American industrial capability. European engineering had failed. European methods had proved inadequate. European equipment had crumbled under tropical conditions. Roosevelt's solution was characteristically American. Don't improve European methods, replace them entirely. In March 1905, Roosevelt appointed John Frank Stevens as chief engineer, bypassing every establishment candidate with impressive credentials. Stevens had never built a canal, never worked in tropical conditions, and possessed only 2 years of formal education from a rural Maine normal school. What Stevens did have was 25 years of railroad construction experience in the American West, where survival depended on solving impossible logistics problems with whatever equipment actually worked rather than whatever European textbooks recommended. Stevens arrived in Panama with a revolutionary philosophy that scandalized European engineering observers. Instead of trying to fix French equipment or replicate European methods under tropical conditions, Stevens placed the largest heavy equipment order in construction history with American manufacturers. 77 Bucyrus model steam shovels, each weighing 95 tons, each costing $25,000, equivalent to $750,000 in modern currency. Each designed not for European precision but for American durability. The specifications seemed impossible by European standards. Where French shovels moved 2 cubic yards per scoop, American Bucyrus shovels moved 5 cubic yards. Where French equipment required 8-man crews working constantly to maintain steam pressure and hydraulic systems, American shovels operated with 4-man crews. Where European machines broke down weekly in tropical conditions, American equipment was designed to operate continuously for months between major maintenance. European engineering publications ridiculed Stevens's approach as typical American excess, disguising fundamental ignorance. The German engineering journal Maschinenbau published detailed calculations proving that Stevens's oversized equipment would sink into Panama's soft soil under its own weight. British railway engineering declared that no steam boiler could maintain adequate pressure in tropical humidity long enough to justify the massive coal consumption Stevens's plan required. When the first Bucyrus shovel arrived at Colon Harbor in August 1905, European skepticism seemed vindicated. Shovel number 222 weighed 95 tons fully assembled, more than 3 times heavier than the largest piece of construction equipment ever successfully operated in Central America. Moving it 20 miles inland to the Culebra Cut required building reinforced railroad bridges and clearing jungle paths wide enough for mechanical transport that had never been attempted in tropical conditions. As tropical rains began falling that October, turning construction sites into muddy swamps that had destroyed French operations, Bucyrus Shovel 222 sat silent under a corrugated iron shelter. Its 4-man crew stared at the mountain of stone and clay that represented their assignment. The French had proven that European engineering excellence could not conquer Panama's geological reality. The untested American approach, with its oversized equipment and systematic methods, faced its first moment of truth in conditions that had already claimed 22,000 lives. The breakthrough came not from a single machine, but from a system that European engineers had never imagined possible. By February 1906, Stevens had orchestrated an integration of American industrial methods that transformed Panama's jungle construction site into the most efficient excavation operation in human history. The 95-ton Bucyrus steam shovels didn't just dig, they operated as components in a mechanical symphony that moved dirt with precision that left visiting European experts speechless. Each steam shovel required a choreographed dance of supporting equipment that Stevens had designed from railroad construction principles. As shovel number 222's bucket bit into Panama's rocky soil, its 4-man crew maintained steam pressure at exactly 160 pounds per square inch, the optimal balance between power and boiler safety that American railroad engineers had perfected over decades of locomotive operation. The shovel's dipper stick reached 30 feet into excavated areas, swinging through a 270-degree arc that European equipment could never achieve without mechanical failure. The genius of Stevens's system revealed itself in the spoil removal process that had destroyed French operations through sheer inefficiency. Where French crews required 45 minutes to load and remove each train of excavated material, American Lidgerwood unloaders accomplished the same task in 8 minutes. The secret lay not in individual machine superiority, but in standardized coordination. Every piece of American equipment, steam shovels, railroad cars, unloading machines, repair shops, operated on identical 4-foot, 8.5-inch standard gauge track that allowed seamless mechanical interaction. Samuel Williams, engineer of Bucyrus shovel number 230, embodied the American systematic approach that European craftsmen found incomprehensible. Williams had learned steam engineering in Pennsylvania railroad yards where locomotives operated continuously for months without major breakdowns. He treated his steam shovel like a precision racing machine, monitoring steam pressure, hydraulic fluid levels, and mechanical timing with scientific attention to detail that European observers mistook for mere enthusiasm. In March 1906, Williams and his crew established excavation records that shocked even American engineers. 1,200 cubic yards removed in a single 10-hour shift. The achievement required perfect coordination between Williams's steam pressure management, his fireman's coal-feeding rhythm, his oiler's mechanical maintenance, and his crane operator's timing with approaching spoil trains. European engineering doctrine insisted that such production rates would destroy equipment within weeks through mechanical overstress. The American machines proved European calculations catastrophically wrong. By maintaining steam pressure within optimal ranges and rotating crews to prevent fatigue errors, Williams's shovel operated at peak efficiency for months without major mechanical failure. The Bucyrus Company had designed their steam shovels using American railroad durability principles, overbuilt components that could handle continuous operation rather than European precision parts that required careful handling. Stevens's mobile workshop system provided the logistical foundation that made continuous operation possible. Instead of shipping broken equipment back to American factories for repair, mobile machine shops followed construction progress along the Canal route. Skilled American mechanics could fabricate replacement parts on site, using standardized specifications that fit every piece of equipment in the system. When shovel number 160 needed a new bucket assembly, Canal Zone workshops manufactured the replacement in 36 hours rather than the 4 months required for European part shipment. The technical superiority of American equipment became undeniable through measurable performance statistics that European engineers could verify independently. Fuel efficiency reached 2.5 tons of coal per 1,000 cubic yards excavated, compared to 4.2 tons required by French equipment under identical conditions. Component durability exceeded all design specifications. Shovel buckets manufactured to last 3 months under tropical conditions were still operating efficiently after 8 months of continuous use. Joseph Buckland, operating shovel number 160, achieved the mechanical miracle that established American engineering credibility permanently. In March 1910, Buckland's crew excavated 70,000 cubic yards in 26 working days, a world record that would stand for decades. The achievement required not heroic individual effort, but methodical precision in steam pressure management, perfect timing coordination with railroad spoil removal, and mechanical maintenance techniques that kept complex equipment operating at peak efficiency under brutal tropical conditions. European engineering delegations visiting Panama in 1910 found their fundamental assumptions about construction methodology completely overturned. Sir William Preece, who had declared American methods systematically inferior, revised his assessment after witnessing Buckland's record-breaking performance. The American systematic approach has achieved what individual engineering excellence could not. Their machines are lasting twice as long as our calculations predicted while moving 3 times more material per day than European equipment. The integrated system's superiority extended beyond individual machine performance to overall project efficiency, that redefined construction economics. By 1910, American steam shovels were averaging 30,000 cubic yards per month per machine, production rates that made canal completion financially viable for the first time. Mechanical reliability reached 85% uptime compared to 40% achieved by French equipment, while repair costs dropped to $1.20 per cubic yard compared to $3.80 under European methods. American steel proved superior to British metallurgy under tropical conditions through systematic testing that European engineers had never conducted. British steel, manufactured for temperate climates, deteriorated rapidly in Panama's humid environment. American steel, developed for railroad construction across diverse climate zones, maintained structural integrity month after month of tropical exposure. The difference lay not in superior ore quality but in manufacturing processes designed for equipment that must operate reliably under unpredictable conditions. President Taft's January 1911 visit to Panama provided political theater that transformed engineering achievement into national pride. Operating Bucyrus shovel number 222 for assembled photographers, Taft declared that American engineering has conquered the impossible through systematic innovation that proves our industrial methods superior to European traditions. Daily excavation across all shovels had reached 300,000 cubic yards, with mechanical availability maintaining 87% of all equipment operational simultaneously, performance levels that European engineering doctrine insisted were mathematically impossible to sustain. The catastrophe struck at dawn on October 1, 1911, just as the Panama Canal project reached its moment of greatest confidence. The Culebra cut stood 85% complete, its walls carved to within 15 feet of final specifications. Daily excavation rates had stabilized at 300,000 cubic yards across all steam shovels, with mechanical reliability maintaining unprecedented levels. Chief Engineer George Washington Goethals had scheduled the official completion ceremony for August 1912, confident that American systematic engineering had conquered every challenge Panama's geology could present. The Cucaracha landslide began with a sound that veteran steam shovel operators would describe as the earth itself groaning under impossible pressure. At 5:47 in the morning, 2 million cubic yards of hillside, an entire mountain face saturated by weeks of tropical rainfall, cascaded into the nearly completed canal, cut with geological violence that dwarfed every previous engineering challenge. The slide moved with terrifying speed, bearing months of excavation under 40 feet of liquid mud and rock debris that stretched for nearly half a mile along the canal route. Bucyrus shovel number 215, operated by engineer Marcus Thompson and his four-man crew, disappeared completely beneath the advancing wall of earth. Thompson had been conducting routine morning maintenance when seismic sensors detected the initial hillside movement. His crew abandoned their positions and ran for higher ground, but the 95-ton steam shovel, America's symbol of mechanical invincibility, vanished under geological forces that reduced industrial achievement to insignificance within minutes. Shovel number 160, Joseph Buckland's record-breaking machine, suffered catastrophic damage that seemed designed to mock American engineering confidence. The slide's leading edge struck the shovel's steam boiler with enough force to crack cast iron components that had operated flawlessly for 5 years under tropical conditions. Buckland's crew escaped injury, but their machine, the mechanical wonder that had established American excavation supremacy, lay twisted and broken under tons of debris that would require months to clear. The psychological impact of the Cucaracha slide exceeded its physical destruction through the cruel timing of geological revenge. 6 months of careful excavation, representing hundreds of thousands of dollars in American industrial investment, had been erased in 48 hours by natural forces that operated beyond human control or prediction. European critics, who had grudgingly acknowledged American mechanical superiority, seized upon the disaster as proof that Panama's geology would ultimately defeat any engineering approach. British engineer Francis Williamson, representing Lloyd's of London insurance interests, arrived in Panama within days of the catastrophe to assess damage claims. His cable to London contained the vindication that European engineering establishments had awaited for 6 years. The Americans have learned what we learned, Nature will have the final word in Panama. The landslides make permanent excavation impossible using any known methods. Systematic planning cannot overcome geological instability. Congressional hearings in Washington questioned fundamental assumptions about the entire canal project with political fury that threatened to terminate American involvement completely. Senator Benjamin Tillman of South Carolina declared that American taxpayers should not subsidize mechanical experiments that ignore basic geological realities. Equipment manufacturers worried that the Cucaracha disaster would destroy their reputations permanently, associating American steam shovels with engineering failure rather than industrial triumph. European engineering publications treated the landslide as scientific validation of their long-standing skepticism about American construction methods. The German journal Zeitschrift für Bauwesen published detailed geological analysis, proving that Panama's shale formations would continue generating massive slides regardless of excavation techniques. French engineering experts calculated that slide clearing operations would cost more money than original excavation, making canal completion economically impossible. Goethals faced the most severe crisis of his military engineering career with characteristic systematic analysis rather than emotional reaction. Instead of abandoning American methods or returning to European approaches, he treated the Cucaracha slide as a design problem requiring innovative solutions rather than project termination. Within 2 weeks of the disaster, Goethals had assembled his engineering staff to develop slide response strategies that transformed geological obstacles into manageable construction challenges. The breakthrough came through geological understanding that European engineers had never developed because their construction projects rarely encountered Panama's unique soil conditions. Goethals recognized that preventing slides was impossible, but responding to slides could become routine through proper equipment positioning and rapid deployment techniques. American steam shovels designed for railroad construction across unpredictable terrain possessed mechanical flexibility that European equipment lacked for crisis response. Terraced cutting procedures, developed through systematic analysis of slide mechanics, reduced geological pressure by 60% through excavation methods that worked with Panama's soil structure rather than against it. Instead of vertical cuts that created unstable cliff faces, American engineers carved stepped terraces that distributed weight loads across wider geological foundations. New drainage systems eliminated water accumulation that triggered most catastrophic slides by channeling tropical rainfall away from excavated areas before saturation could destabilize hillsides. Steam shovel repositioning became a mechanical specialty that transformed crisis response into routine operational procedure. American crews developed techniques for moving 95-ton machines across difficult terrain in 4 hours rather than the weeks required under normal circumstances. Slide clearing operations use specialized bucket configurations designed specifically for moving liquid mud and rock debris rather than the normal excavation work that had established original performance records. The recovery statistics proved American engineering resilience through measurable results that European critics could not dismiss. By December 1911, 95% of lost excavation had been recovered through systematic slide clearing operations that maintained normal construction schedules. Shovel reliability during crisis response actually improved to 91% uptime as crews developed emergency maintenance procedures under pressure conditions that revealed equipment capabilities beyond original design specifications. Cost impact remained minimal despite catastrophic initial damage, with total project overruns reaching only 12% above original budgets. European engineering consultants had predicted that major landslides would generate 200% cost increases that would make canal completion financially impossible. American systematic methods, adapted for geological crisis management, proved capable of absorbing natural disasters without fundamental project disruption. The Cucaracha slide ultimately strengthened American engineering credibility by demonstrating adaptability under extreme conditions rather than mechanical failure. European methods designed for predictable geological conditions offered no solutions for unprecedented challenges. American systematic approaches, developed for frontier construction across diverse terrain, provided the flexibility necessary for success under circumstances that no previous engineering project had encountered. The engineering revolution that emerged from the Cucaracha disaster transformed American steam shovels from excavation equipment into geological crisis specialists with capabilities that European engineers had never imagined possible. By January 1912, Goethals had redesigned canal construction around the revolutionary principle that landslides were not obstacles to overcome, but predictable events to manage through systematic preparation. American crews developed slide response protocols that turned catastrophic geological events into routine operational challenges, requiring specialized techniques rather than project termination. Rapid deployment became a mechanical art form that showcased American industrial adaptability under extreme conditions. Steam shovel crews could disassemble, transport, and reassemble 95-ton machines across unstable terrain in 4 hours, using standardized procedures that European observers found impossible to believe without witnessing personally. The secret lay in modular construction techniques borrowed from American railroad engineering, where locomotive repair required rapid component replacement under field conditions that offered no access to workshop facilities. Specialized slide-clearing bucket configurations transformed standard excavation equipment into geological emergency response tools with capabilities far beyond original design specifications. American manufacturers developed bucket assemblies with reinforced cutting edges and enlarged capacity specifically for moving liquid mud and rock debris rather than normal soil excavation. These modifications increased bucket weight by 30%, while maintaining structural integrity under impact loads that would destroy European equipment designed for careful digging rather than crisis response. Predictive maintenance under crisis conditions revealed mechanical capabilities that peacetime operation had never tested fully. Steam shovel crews working continuous shifts during slide clearing operations discovered that American equipment could sustain peak performance levels for weeks without major component failure when properly maintained using systematic procedures. Boiler efficiency actually improved under sustained operation as crews developed steam pressure management techniques that optimized fuel consumption while maintaining maximum hydraulic power output. The January 1912 performance statistics proved American engineering superiority through crisis response rather than normal operation success. During the most intensive slide clearing month in canal construction history, mechanical reliability reached 91% uptime across all steam shovels, higher than peacetime averages achieved under optimal conditions. Equipment operated continuously for 18-hour shifts with only brief maintenance intervals, moving debris at rates that exceeded normal excavation records established during routine construction periods. American steel performance under extreme stress conditions vindicated metallurgical decisions that European critics had questioned from project inception. British steel components, manufactured for temperate climate operation, failed catastrophically under the combined stress of tropical humidity and emergency operational demands. American steel, developed for railroad construction across diverse environmental conditions, maintained structural integrity month after month, despite mechanical loads that exceeded original design specifications by substantial margins. Cost efficiency during crisis response demonstrated systematic economic advantages that made American methods financially superior to European alternatives under any operational conditions. Slide clearing operations cost $1.40 per cubic yard compared to $2.60 that European consultants had calculated for equivalent emergency response using traditional methods. American equipment durability under extreme conditions eliminated replacement costs that European crisis response would have required through mechanical failure rates. The engineering breakthrough that secured permanent American credibility came through geological understanding combined with mechanical innovation that European construction methodology had never integrated successfully. Instead of treating slides as construction failures requiring equipment replacement, American engineers redesigned excavation strategies to incorporate slide response as normal operational procedure. Steam shovels became geological management tools rather than simple digging machines, operating according to systematic protocols that transform natural disasters into manageable construction challenges. President Taft's return visit in March 1912 provided political theater that transformed engineering achievement into national industrial pride on a global scale. operating the same Bucyrus shovel number 222 that had survived the Cucaracha slide, Taft declared to assembled international reporters that American systematic engineering has proven superior to European methods through adaptability under conditions that would have terminated any previous construction project in human history. The final construction statistics validated American industrial methodology through measurable results that European engineering establishments could no longer question or dismiss. Total canal excavation reached 240 million cubic yards using 102 steam shovels that had moved 200 million cubic yards while maintaining mechanical reliability rates exceeding original design specifications. Project completion occurred 6 months ahead of revised schedules, despite catastrophic geological setbacks that European consultants had predicted would require decades of additional construction time. European acknowledgement of American engineering supremacy came through institutional recognition that represented fundamental shifts in global construction methodology. The British Institution of Civil Engineers awarded its highest honor to the Panama Canal project in July 1914, specifically citing the revolutionary application of American steam excavation technology that has established new standards for mechanical reliability and systematic crisis response under extreme environmental conditions. The canal opening ceremony on August 15, 1914, marked the triumph of American systematic engineering over European traditional methods through demonstrated superior performance under the most challenging construction conditions ever attempted. The first ocean-going vessel to transit the completed waterway passed between excavated walls carved entirely by American steam shovels, operating according to systematic maintenance and operational procedures that had sustained peak mechanical performance for nearly a decade of tropical construction. Final engineering assessments proved that American equipment had exceeded every performance specification while operating under conditions that European methodology considered impossible for sustained mechanical operation. Average steam shovel service life reached 45 years, with total excavation exceeding 2 million cubic yards per machine. Maintenance costs over operational lifetimes remained lower than European equipment replacement cycles, validating American durability philosophy that emphasized long-term mechanical reliability over initial precision manufacturing. The Panama Canal steam shovels established American industrial engineering as the global standard for systematic construction methodology that integrated mechanical excellence with operational flexibility under unpredictable conditions. European engineers adopted American systematic approaches rather than defending traditional methods that had proven inadequate for large-scale construction projects, requiring sustained mechanical performance under extreme environmental stress. The excavation equipment that had seemed impossibly oversized by European standards in 1905 had become the mechanical foundation for the most successful engineering project in modern history. The Panama Canal steam shovels didn't retire when the last ship passed through the completed waterway in August 1914. They dispersed across the globe to begin second careers that would prove their durability philosophy in ways their original designers never anticipated. Bucyrus shovel number 160, Joseph Buckland's record-breaking machine that had survived the Cucaracha slide, found new life in Alaska's Kennecott copper mines where sub-zero temperatures and permafrost created mechanical challenges as severe as Panama's tropical humidity. The same steam boiler that had maintained optimal pressure through 5 years of jungle excavation operated flawlessly through 41 years of Arctic mining operations. Railroad construction projects across South America absorbed dozens of canal shovels that continued excavating mountain passes and valley cuts with the same systematic reliability they had demonstrated in Panama. Shovel number 230, Samuel Williams's early record setter, carved railroad grades through the Andes Mountains until 1962, moving an additional 800,000 cubic yards of rock and soil during its extended service life. The machine that European critics had declared oversized for tropical conditions proved ideally suited for high-altitude construction, where thinner air reduced steam efficiency and mechanical stress exceeded original Panama specifications. Ohio strip mining operations purchased canal shovels throughout the 1920s and 30s. discovering that equipment designed for systematic excavation in unstable geological conditions excelled at coal extraction in the American Midwest. Mining companies reported operational costs 30% lower than comparable European equipment while achieving production rates that exceeded modern standards. Some units remained operational until 1970, accumulating total service lives approaching 60 years of continuous industrial use under diverse environmental conditions. The engineering irony became apparent during the 1930s. Economic depression, when steam shovel operational costs finally exceeded their productivity value through changing economic conditions rather than mechanical failure. Diesel engines offered 50% lower fuel costs per cubic yard excavated while requiring simplified maintenance procedures that eliminated specialized boiler operators and steam engineers. Modern hydraulic systems provided faster cycle times and reduced crew requirements from 4 men to 2 men per machine, creating labor savings that made steam power economically obsolete despite superior mechanical durability. What ended the steam shovel era wasn't mechanical breakdown, but systematic economic replacement by technologies designed for profitability rather than longevity. Diesel-powered equipment eliminated the 45-minute steam raising time required for daily startup, allowing construction crews to begin excavation immediately upon arrival at work sites. Hydraulic systems responded instantly to operator commands without the careful pressure management and timing coordination that steam operation required from skilled crews trained specifically for complex mechanical systems. The transition revealed fundamental differences between American and European engineering philosophy that the Panama Canal project had established permanently. American equipment manufacturers had designed steam shovels for maximum operational lifespan using overbuilt components that could sustain decades of continuous service under extreme conditions. European manufacturers focused on initial efficiency and precision operation that required replacement when changing technologies offered superior performance characteristics rather than extended mechanical durability. Maintenance cost comparisons over complete operational lifetimes vindicated American durability philosophy through measurable economic data that industrial historians would study for decades. Steam shovels averaged 22 cents per cubic yard in lifetime maintenance costs compared to 38 cents for diesel equipment replacement cycles over equivalent service periods. Parts availability for steam shovels remained consistent for 40 years through standardized component manufacturing, while modern equipment became obsolete when computer control systems failed after 10 to 15 years of operation. The lasting proof of American engineering superiority emerged through unexpected longevity testing that occurred naturally as steam shovels outlasted the economic systems that had created them. Canal construction had required equipment capable of sustained operation for a decade under tropical conditions. The shovels that accomplished this goal continued operating for additional decades under diverse environmental challenges that tested mechanical limits far beyond original design specifications, while maintaining productivity levels that exceeded modern replacement equipment. Modern hydraulic excavators, marvels of computer-controlled precision and fuel-efficient operation, revealed the planned obsolescence philosophy that governed contemporary equipment manufacturing. Advanced machines designed for optimal short-term performance typically achieve 10,000 hours of operation, equivalent to 5 or 6 years of heavy construction use, before requiring complete replacement rather than major component repair. Electronic control systems, hydraulic pumps, and precision machine components were manufactured for replacement rather than indefinite repair using field maintenance techniques. The 1999 Panama Canal Authority Equipment Assessment provided the ultimate vindication of American steam shovel durability, when maintenance crews discovered 3 original Bucyrus shovels stored in Canal Zone warehouses after 85 years of inactive storage. Mechanical inspection revealed that steam boilers, hydraulic systems, and structural components remained sound enough for restoration to operational condition using standard repair techniques and readily available replacement parts manufactured to original specifications. The engineering lesson transcended simple mechanical comparison to illuminate fundamental philosophical differences about industrial design that separated American and European approaches to construction equipment manufacturing. American steam shovels had been built according to railroad durability standards that emphasized indefinite operational capability under unpredictable conditions through systematic over-engineering of critical components and standardized maintenance procedures that field crews could execute without specialized factory support. Modern excavation equipment reflected economic priorities that emphasized optimal performance per dollar, invested rather than maximum operational lifespan or field repairability under adverse conditions. Contemporary machines achieve superior fuel efficiency, faster cycle times, and reduced operator skill requirements while accepting planned obsolescence as an economically rational design philosophy that generated recurring equipment sales rather than extended service life through systematic maintenance and component replacement. The final irony revealed itself through historical comparison between Panama Canal construction costs and modern excavation project economics that demonstrated the long-term financial advantages of durability-focused engineering despite higher initial equipment investment. Canal steam shovels had moved 200 million cubic yards using 102 machines that operated for an average of 45 years each, creating a total system cost per cubic yard that remained lower than any subsequent large-scale excavation project, despite dramatically higher labor costs during the steam era. The American steam shovels that had proven European engineering doctrine wrong in Panama's tropical mountains became symbols of an industrial philosophy that prioritized systematic durability over immediate efficiency, establishing mechanical standards that modern equipment manufacturers abandoned in favor of planned obsolescence and recurring replacement cycles that generated continuous revenue streams rather than indefinite equipment service life through systematic maintenance and field repair capabilities.